Hey guys, in this video I'm going to be reviewing chapter 3. So there's basically just two concepts that are really important in chapter 3, and they are nuclear equations and half-life. So with nuclear equations, you just need to be able to complete these, and we did this before. It's pretty easy because the concept is that the mass numbers, remember the mass number is the top number, the mass numbers on the left have to add up to the same thing that the mass numbers on the right add up to. So on the left we have 9 and 1, so that's 10. So over here we have 4, so the question is 4 plus what is 10? And obviously it's 6, so this is going to be 6. And then the same thing is true of the numbers on the bottom, which are called the atomic number. Again, that's the number of protons. And on this side, we've got 4 and 1, so that's 5. So we need it to be 5 over here. We've got 2, so obviously 2 plus 3 is 5. So now we've got our two numbers. To figure out what element that is, we just look on the periodic table for element number 3. It's lithium. And so we just write Li. And then you can check and make sure that they add up, and they do. And that's it. So that's how you complete nuclear equations. Okay, let's talk about half-life now. So what is half-life and how can you change it? So the half-life is the time it takes for 1/2 of a radioactive substance to decay. So let's say I have 100 grams of something radioactive. After one half-life, 50 grams will still be radioactive and the other 50 grams will have turned into something else. Can I change the half-life? No. There's nothing that can change the half-life. Temperature, pressure, concentration, none of those things affect the half-life. So, can't change the half-life. Can't change the time it takes for the substance to decay. Okay, so that's just conceptually what half-life is. You also need to be able to solve problems with half-life. And again, we've done this before this year, so this is just a review. This first problem says the half-life of AC-225, so that's just some radioactive isotope, is 10 days. If we start with a 100-gram sample of AC-225, how much will remain after 50 days? So you might remember that the easiest way to solve these problems is to do a time and amount table. And you might also remember that we always start at time 0, that's like the beginning, and then we start with our initial amount. So it says we start with 100 grams. And then it tells us that the half-life is 10 days. So after 10 days, half of it will still be radioactive, so 50. And we count by tens. Remember, on the time side, we don't double, we count by the half-life. So I need to go all the way down to 50 because it wants to know how much will remain after 50 days. So it's going to be 25, 12.5, 6.25, 3.125. So the amount after 50 days that's still radioactive would be 3.125 grams. The rest will all be not radioactive anymore. Okay, another problem with half-life. How many years old is a fossilized tree that contains 25% of its original carbon-14? The half-life of carbon-14 is 5,730 years. So this one is similar to the one before, but there's something a little bit different. I'm going to start at time 0 again. Always start at time 0. That never changes. And then the next thing is going to be the half-life. Now the tricky thing is that they didn't give me an initial amount. They didn't tell me how much I'm starting with. But since I'm talking about percentages here, I can just assume that I started with 100%. So if I started with 100% after one half-life, I'll have 50%. And after another half-life, which if I'm adding this right in my head, would be that number, I'll have 25%. So the tree would be 11,460 years old. Now, if you're not using percentages, you can also do this with fractions. So if you're using fractions, you would actually start with just 1, and then 50% is 1/2, 25% is 1/4, etc. So if it doesn't give you an initial amount, use fractions or percentages to figure out your answer. So that's chapter 3 in 5 minutes.